notes and we'll start conference.
Good afternoon, sir.
Good afternoon. Just wait. I'm going to share my notes. Is it visible to you, Sri?
Visible, sir.
So one more chapter. We are going to discuss about solid state chemistry, which contains even nanomaterials part also. So what are meant by solids? The solids are having a very closely structured materials which are quite different from the liquids and the gases. The density of the solids also will be very high and they may possess ordinance materials. The ordinance will be very high. So then there are two kind of solid materials will be there. Crystalline solid materials and the amorphous solid materials. Just a brief introduction about solids. Crystalline solids and amorphous solids. In crystalline solids, so they can possess a sharp melting points. But in amorphous, the melting points will be within a range of temperatures. So during the temperature range, we can get amorphous solids. But in case of crystalline, that is at a sharp melting points. The sodium chloride example is the solid material. That is the sodium chloride crystal can be formed. Then amorphous solids will be glassy materials or plastics or rubbers. These all are examples for the amorphous materials. Okay. And one more thing here, solids are perfectly ordered materials. If you may consider the entropy of all those things or any thermodynamic property for the solids, that will be less compared to liquids compared to gases. Gases molecules are randomly distributed in nature. Therefore, the more randomness becomes, entropy will be more. With the help of the corresponding, we can get less entropy of the solids. Even we can discuss about the third law also. The entropy of a perfect crystalline material becomes zero, right? So that is also we have to applicable for the solid substances. Apart from that, so in our syllabus, there is a band theory will be there. So what is meant by band theory? How we are getting various kind of the materials like conductors, semiconductors, and insulators. The conductors, semiconductors, and insulators that are particularly or purely based on nature of the valence band and conduction band. So therefore, the band theory is going to explain about how the band formation will be takes place. Right. So let's see. So the scientist Walter Hitler and Kate Landon so discovered a very closely spaced energy levels. So means the energy levels are very closely spaced. Just we have to observe this diagram, right? If you observe this diagram, so this is in case of sodium, right? If one energy level will be there, the outermost electron will be only one electron. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Outermost shell is the 3s. In that outermost shell, there is only one electron. Like that, so if two sodium molecules are come closer together, so that can overlapping of those 3s orbitals, you can get two molecular orbitals. The overlapping phenomena is based on the linear combination of atomic orbitals. So two atomic orbitals of 3s orbitals of sodiums are overlapped with each other are involved in a combination method, we can get two molecular orbitals. One is a bonding molecular orbital and other is a anti-bonding molecular orbital. So like that, the various number of sodium atoms are involved, right? So we can get various energy levels, right? So these all are various energy levels we are getting. So as this all energy levels are come closer together, that can make a bond. So this is with the help of valence shell, there is a making of band. So therefore that particular band is known as what? Valence band. Valence band means it is a very closely spaced energy levels which are kept as a band. Such band is known as valence band. So in valence band is a fulfilled with electrons or half filled with electrons. Definitely electrons should be present in the valence band. Then in sodium, after 1s1, 1s2, 1s2, 2s2, 2p6, 3s1, another 3p orbitals will be there. Those 3p orbitals are also involved in linear combination method, so they can also form some energy levels. Therefore, the NP band means all the 3p orbitals of sodiums are involved in making a band. Such band is known as conduction band. Right? So here we have to see. So this is the one of the band. So then conduction band will be with the help of valency means 3p orbitals, we can get conduction band. Based on these bands, conduction band and valency band, so we can get a three kind of materials, right? So once those two are overlapped, right? You may observe this one. You may observe this one. This is the what? Overlapping of the conduction band and the valence band. So once the overlapping of conduction band and valence band, there is a promotion of electron from 3s1 to 3p is very easy. As the electrons are promoting from valence band to conduction band, but due to conduction, due to promotion of electrons, that will be conductivity. Such type of materials are known as conductors. Simple here, we have to remember conductors means the overlapping, sorry, promotion of electrons from valence band to conduction band easily when the conduction band and the valence band are overlap with each other. So this is due to this overlapping. So valence electrons will be easily moved into the conduction band. Right? So based on that, we can get the various type of the substances, right? So that are conductors, insulators, and semiconductors. Right? So the conclusion of band theory, various sodium metals are involved in making of a crystalline structure, making of a crystalline structure in which right, outermost electrons are involved in making of a band. Such band is known as valence band. Valence band is filled with half filled with electrons, or sometimes it is full filled with electrons. For example, in sodium, only one electron is there. Like 10 number of sodiums are involved, 10 electrons we will get. All those 10 electrons will be occupied 5 energy levels because electrons are paired up. For example, if you take magnesium, 2s2 will be there. So in the 2s2, right, 10 magnesium means 20 electrons will go. Therefore, all those 20 electrons you have to arrange it in the energy levels means all the valence band energy levels are filled with electrons. So that's why valence band is either filled with electrons or half filled with electrons. Then coming to the part of conduction band. The conduction band is always either empty band or that is also partially filled with electrons. Because so when it should be empty band, right? When it should be empty band. You see, empty band means if without electrons, those orbitals are involved in making of the band, that is the empty band. For example, if any element is consisting with one electron, remaining if that is present in pz orbital, remaining px and py will be there. Those px and py orbitals are overlapped, that can give empty band. If including this p orbital also will be overlapped partially containing electrons. So therefore, conduction band is a empty band or partially filled with electrons. Now, based on the nature of this, right, if you observe this diagram, right, there is some energy level, right, there is some energy level gap between the valence band and conduction band. If you see here, so this is the above one is the valence band, below one is the conduction band. If this valence band and conduction bands are overlapped, this is the word conduction band, this above one is the valence band. So sorry, below one is the valence band, above one is the conduction band. So when these two are overlapped, valence band is overlapped with conduction band, so the electrons will be easily promoted from valence band to conduction band. Right? Hence, such type of materials are known as conductors. This is happened in metals. The conductors are metals. Metals are the conductors. They consisting surface electrons. So those electrons are promoted from one energy level to next another energy level. Whenever these two bands are arranged with a small gap, conduction band and valence band, these two are arranged with a small gap. Therefore, whenever small gap is there means a few number of electrons are moved from valence band to conduction band. Right. So here is the new gap is there between these. This is the conduction band, and this is the valence band. This is the valence band. In between this valence band and conduction band, there is a gap is very small. When small gap is there means few electrons are transferred from valence band to conduction band. Therefore, that can give little bit conductivity. Such type of materials are known as semiconductors. Then coming to the last one, there is a gap between conduction band and valence band is very high. So due to very high band gap energy, the electrons cannot be promoted from valence band to conduction band. The electrons may not promote from valence band to conduction band. Hence, they are called as insulators. There is no promotion of electrons from valence band to conduction band. Therefore, that are called insulators. Right? So, based on these energy level diagrams, we have to understand that materials are three types. From the band theory, so we are getting conduction band and valence band. Valence band is a filled with electrons or half filled with electrons. Conduction band is a empty band or half filled with electrons or partially filled with electrons. When these two are arranged with some energy level gap, these two are arranged with some energy level gap. So that is based on that we have to divide the various materials. One is the conductors. In conductors, conduction band and valence band are overlapped with each other. Next, in semiconductors, valence band and conduction bands are separated with a small distance. In insulators, valence band and conduction bands are separated with a large distance. Hence, with the help of this, we can get the kind of materials that are conductors, semiconductors, and insulators. So just we will go through the definitions. Right. So conductors also, you'll be able to see this diagram also. Conductors will be overlapped. Semiconductors will be small energy gap, and insulators will be large energy gap. In insulators, the large energy gap will be called as forbidden energy gap. Therefore, no promotion of electrons from those valence band to conduction band. Right? So based on that, we can get three kind of materials, right? One is the conductors and another one is the insulators. Then coming to the part of middle one, that are semiconductors. So here we have to discuss about semiconductors in detail because there is a semiconductors means the materials in which valence band and conduction bands are separated with a small distance. Such materials are known as what? Semiconductors. So such materials are known as semiconductors. In this, a very few number of electrons are transferred from valence band to conduction band. Therefore, these are semiconductors. Few conductivity will be there. That is called semiconductors. So these semiconductors are again two types. Right? One is intrinsic semiconductors and other one is the extrinsic semiconductors. Intrinsic semiconductors and extrinsic semiconductors. What is meant by intrinsic semiconductors means the semiconductor material is made up of the same kind of elements. There is no impurities are present, pure elements are involved. The fourth group elements are forms semiconductors like silicon and germanium, in which in which each silicon is bonded with another four silicon atoms. Each silicon atom is bonded with another four silicon atoms. Like that, many number of silicon atoms are joined together that will make a material that is known as intrinsic material. Right? So such conductors are known as intrinsic semiconductors. In this intrinsic semiconductors, right? So the electrons promotion from valence band to conduction band takes place, hence they are semiconductors. Then one more will be extrinsic semiconductors are there. If it is a pure form, that is the intrinsic semiconductor. If it is a impure form, that is the extrinsic semiconductor. Whether it is a pure form, the material is a pure form material, that is a conductor, means intrinsic semiconductors. There are some impurities will be there. How we are getting impurities in that material? If one of the silicon atom is replaced with other element, one silicon atom can be replaced with other elements. Those other elements may be having more electrons compared to silicon or less electrons compared to silicon. Based on the dopants, what kind of element we are doping in place of silicon, so we can get another two type of extrinsic semiconductors. Extrinsic semiconductors are impurities only, intrinsic semiconductors only, pure form only, right? So these extrinsic semiconductors, again, two types. One is N type of semiconductors and P type of semiconductors. Right? So just we'll go through it. Semiconductors and intrinsic and extrinsic will be there. In intrinsic, there is a pure form is present. In extrinsic, there is a impurities are present. Based on these impurities, so just here we have to observe the diagram. This is the one of the silicon atom. This is the one of the silicon atom is bonded with four other silicon atoms. Like this is a silicon atom bonded with other four silicon atoms. This is the bonded atom with the other four silicon atoms. Like that, if you knew, in this place, one of the silicon atom is replaced with phosphorus or arsenic. So what about the phosphorus and arsenic? Phosphorus and arsenic will be consisting five electrons. But here for bonding, only four electrons are required. So these four electrons are making bonding and the fifth electron will be present. This fifth electron will be excess electron. Like that, many number of silicon atoms are replaced with it. Many number of silicon atoms are replaced with it. Many number of fifth group elements like pentavalent impurities like phosphorus or arsenic. Fifth group element. Fifth group element is consisting of 5 electrons in their outermost shell. The 4 electrons will be bonded, making bonding with silicon atoms. The other fifth will be takes place at interstitial part only. Like that, by replacing one atom, one electron we will get. If you replace many number of atoms, we can get many number of electrons. All those electrons are creating one discrete energy level. So for example, 10 electrons will be 10 elements will be doped with pentavalent elements, like fifth group elements, or else one of the silicon atom is replaced with fifth group elements, 10 electrons will get. All those 10 electrons are making as a discrete energy level. So that discrete energy level is just about the just below to the convection band it will be happening, right? So if you see the diagram, here you have to observe. This is the circles will indicate what discrete energy level. So this discrete energy level just below to the convection band. How much distance it is? 0.1 electron volts. Just 0.1 electron volts below to the conduction band. Therefore, it is easy to get a conduction of electron from this energy level to conduction band. Do you think that If electron will be enters from valence band to conduction band, that is difficult because there is a gap is small. But the electron will be from discrete energy level to conduction band, that is very easy. Let's see here. This is the electron will be moving from here to here, or the electron will be moving from here to here. So out of these two possibilities, the electron will be moving from discrete energy level to the conduction band is very easily. Hence, this will show more conductance compared to this. The reason was N type of semiconductors, right? N type of semiconductors are prepared by replacement of one silicon atom with a fifth group elements. Those fifth group elements are like phosphorus and arsenic and etc. So this is the thing, right? As impurities will be present, means doping, so we can get the increasing the conductivity of the semiconductors. So then coming to the type of P type, right? The same thing we have to discuss, but here the replacement of one silicon atom. Right? So this is the one silicon atom. This is the one silicon atom surrounded with four other silicon atoms. This is the one silicon atom surrounded with four other silicon atoms like that. So there is a formation of a solid substances takes place, in which one of the one of the silicon is replaces with a third group element. What about the third group elements? Boron and aluminum. If we have to replace one position of silicon with one bromine or aluminum, what will happen? To make a bonding with silicon, other silicon atoms, 4 electrons are required. But here it has third group element only 3 electrons. Therefore, one hole can be found. This is that for hole. Means this is a vacant position will be there. If we replace one element with third group element, one hole we will get. Like many number of atoms are replaced with third group elements, many number of holes we will get. Therefore, those all the holes are making a discrete energy level that is just about the valence band. See, so here we have to observe that, yeah, view, right? So this is the conduction band, this is the conduction band, and this is the valency band. This is the valency band, right? So just the holes we are getting means those holes are creating one energy level that is just about the valency band. Hence, the electrons will be promoted from valence band to conduction band is very easy as compared with the valence band to conduction. Compared with this, right? So from valence band to conduction band, there is a large gap is there. Therefore, it is difficult to get the electron from valence band to conduction band. But whenever some of the atoms are replaced with other elements like third group elements, there is a formation of holes will be takes place. Those holes are making a discrete energy level that is just about to the valence band. Just about to the valence band. Hence, the promotion of electrons from valence band to these energy levels, it will be very easy as compared with the valence band to conduction band. So that's why with the impurities of semiconductors, right? In semiconductors, they are adding impurities. Those impurities are increasing the conductivity of the semiconductor. Increasing the conductivity of semiconductors. Hence, the conductivity of semiconductors are increases with the dopings. Right. Whether we go with either P-type semiconductors or go with N-type semiconductors. Semiconductors means all the silicon atoms will be making as a crystal structure, right? The solid material, in which one of the silicon is replaces with either N-type semiconductor or P-type semiconductor. If fifth group elements are replaced by silicon atom, we can get N type of semiconductors. If fourth group elements are replaced by semiconductors, holes we are getting as a result. Therefore, that is called as positive. That is positive means P type of semiconductors. In both the cases, P type and N type semiconductors, the conductivity is decreases. Hence, in semiconductors, with the help of dopants, particularly in extrinsic semiconductors, the conductivity will be increases. Yes. So once again, what we have discussed here, one is the particular band theory. Band theory means how the bands are taking place. What is the valency band? What is the conduction band? If valency orbitals are involved in making a p band, that is the valence band. If empty orbitals or next orbitals are involved in making of band, that becomes conduction band. Based on this conduction and valence band, if they are overlap with each other, that are called conductors. If the two are separated with a small gap, that is semiconductors. And if the two are making arrangement with large energy gap, that are insulators. In insulators, no promotion of electrons from valence band to conduction band. Semiconductors, only few electrons are promoted. And in conductors, many number of electrons are promoted from valence band to conduction. The semiconductors are again two types. One is the intrinsic semiconductors and extrinsic semiconductors. Intrinsic means only pure, extrinsic means impurities. One of the silicon atom is replaced with the other elements like fifth group elements are third group elements. Fifth are third. The fifth group elements will be doped with silicon or in place of doping at in place of silicon. You can get N type. The third group elements will be doped, that will be P type semiconductor. Right. After that, the effect of temperature. The effect of temperature of conductivity of extrinsic semiconductors. So particularly we have to see the effect of temperature. Generally in case of conductors, what will happen as the temperature is increases, right? Between the collide particle, between the particles collisions will take place. One second. So between the molecules, some collisions are takes place. Due to the collisions, the velocity of the ions will be decreases. So therefore, hence the conductivity is decreases. That is, if you see, with increasing the temperature, right, increasing the conductivity is due to extra electrons jump into conduction band. In case of intrinsic semiconductors, only pure are there. For example, silicon. Silicon is bonded with another four silicon atoms. Like that four again bonded with another four silicon atoms. Therefore, here, whenever it is a pure form, the electrons, extra electrons will be jumped into the next energy level, next conduction band level. Hence, with respect that as the temperature is increases, intrinsic semiconductor conductivity also increases. But this is the reverse to the extrinsic semiconductors. For extrinsic semiconductors, if we increase the temperature, the collides takes place between the molecules. Right? So between the molecules, there are some collision will be there. When molecules are involved in collision, the velocity or mobility or speed of the molecule ion will be decreases. So therefore, hence conductance is decreases. So as increasing the temperature, right? In extrinsic semiconductors, just go to it. In extrinsic semiconductors, the conductance. In extrinsic semiconductors, there is a decrease in the conductivity due to increase in the temperature. Once the temperature increases, there are increasing the vibrations in the semiconductor atoms. So therefore, simply here we have to understand in intrinsic semiconductors, the conductivity is increases as temperature is increases. But in extrinsic semiconductors, conductivity is decreases as temperature increases. This is the temperature increases. The temperature increases in intrinsic conductance also increases. This is the conductance. This is the conductance. Right. In intrinsic semiconductors, conductance is decreases as temperature increases. So this is the thing, and that should be explained with the help of an equation. So that is called, right? That is called sigma is equals to 2 into, right? This is the equation can be used to express, right? Mobility of the electrons and holes. Sigma is equals to into mu plus P into ut. And n are the number of electrons, P is the number of holes, right? Then rho is the density and all those things. This is in case of intrinsic and extrinsic semiconductors. Intrinsic and extrinsic. But extrinsic is again how many types? Two types. That is N type and P type. In that, what will happen? Okay. Effect of temperature and doping on mobility of a semiconductors. If we have to dope with other elements in place of silicon pure elements, silicon and germanium, right? So the conductance will be varying with respect to the function of temperature. That is, sigma is equal to Q into mu n into Tn into T plus mu P into Pp into. So this is the equation will indicate how the temperature will be affecting on coating of semiconductors, which leads to the change of their conductivity values. Right? So just these things we have to understand with the help of one diagram. You see here that impurity scattering will be there and lattice scattering will be there. Right? If we may discuss, this is the left hand side is the impurity scattering, right hand side will be lattice scattering. So this is the temperature scale. Therefore, here, so some curve we are getting instead of this maximum value, that will be equals to t power 3 by 2 here and t power minus 3 by 2 here. And also, the temperature dependent semiconductor equation also should be expressed in the form of like this. So that is n of t is equals to into 2 pi kt by h square power 3 by 2 into mn power mp dot power 3 by 4 and the exponential power minus eg by 2k. So in which the mobility of the ion is directly proportional to what? Exponential power minus eg by 2kt. So as based on this exponential power, so we can get the conductivity changes with respect to temperature. So this is the effect of temperature. This is the effect of temperature on intrinsic and extrinsic semiconductors. Temperature effect on intrinsic and extrinsic semiconductors. Therefore, here we have to discuss about what some small topic that is excitons. So, what are meant by excitons? An exciton is a bound state of an electron and a hole which are attracted to each other by the electrostatic. It is a bound state of electron and a hole, right? So the bound state of electron and hole, that is clearly what electrostatic force. So that will gives excitons. It is electronically neutral quasi-particles that exist in insulators, semiconductors, and in some liquids. So in both semiconductors and insulators, the excitons will be produced. The exciton is elementary excitation of condensed matter that can transport energy without transporting net electrical charge. So without changing that net electrical charge, right, that can be explained. Coming to the part, what is meant by exciton? Just see here. This is the positive charge. Nucleus will be there. Nucleus will be positive charge, and electron will be revolving around the nucleus like that. So here is the electron nucleus. So the electrostatic force of attraction between positive and negative, so that can give excitons. This can give excitons. Then here one more topic is there. We have to discuss about photoconductivity. What is meant by photoconductivity? It is simple. We have to understand that from easily. Right? The phenomenon of increasing of conductivity of a semiconductor due to absorption of light radiation. So we have a semiconductor. We have a semiconductor whose semiconductor conductance will be increases, that is with the help of light radiation. That is called photoconductivity. Means the material is exhibiting conductance. The material is exhibiting conductance. That conductance will be with respect to the photon, that is light radiation. How much intensity of light is incident on that material, how they become, right, how they become produces conductivity. So that will be known as photoconductivity. The phenomenon of photoconductivity will be explained also, right? Explained also with the help of, right, this. What is meant by this means whenever light radiation is incident on the substance, the electrons will be promoted from valence band to conduction band. Therefore, that can be produces conductivity. Conductivity. So this conductivity we have to get in semiconductors or materials. So what was the condition is applicable for that? The condition which is applicable for that, whatever the light is incident on the material, that must be higher than the energy gap between the valence band and conduction band. Just you go through this condition, like H nu is greater than Eg. Eg is the energy gap between the valence band and the conduction band. You have to provide that energy more than that only, then only the electron will be promoted from valence band to conduction. Suppose we have given less energy to this system compared to energy gap, but electrons do not get sufficient energy to get promotion from valence band to conduction band. Therefore, the condition for photoconductivity is maybe that is either equals to or greater than, right? So therefore that will be, we have to written as H nu is either equal or greater than to the Eg, energy gap. Whatever is the energy gap between the conduction band and valence band is there. So we have to supply that energy, light energy to this subject, right? So that is either more than or equal. Then only electron promotion will be takes place. Hence, that will shows photoconductivity. So this is the most important thing we have to understand photovoltaic effect also. So what is meant by photovoltaic effect? With the help of that, we can get diodes and transistors. There are huge applications of diodes and transistors will be there, right? So NPN transistors, PNP transistors, and the photovoltaic effect, all we are going to discuss. See, this is the first experiment done by French physicist, that is Becquerel. Not Becquerel. Photovoltaic effect experimentally demonstrated by Becquerel. What he is observed that means, right? So previously Albert Einstein proposed that quantum theory of light and explained the photoelectric effect. So according to Einstein, what is the photoelectrical effect means? Whenever, whenever the light is incident on the metal surface, metal has already electrons on the surface. Those surface electrons are get ejected. Right? So those surface electrons will be gets exalted, means ejected. That ejection of electrons from the surface of the metal is known as photoelectric effect. So with the help of based on that photoelectric effect, photovoltaic effect was demonstrated by Becquerel. So what is meant by this means the creation of voltage and electric current in a material. In a material, we have to create voltage, right, or electrical current when that material is exposed to light and a physical and chemical phenomenon. The best example will be solar cells or the building blocks of photovoltaic molecules. The solar cells. This photovoltaic effect includes, right, photovoltaic effect includes the various properties that are absorption of light and generation of electron hole pair. And there is a separation of charge carriers of opposite types. If you have to separate the charge carriers, and that we can get information. The separate extraction of those carriers to an external circuit. So these are the parameters which will be included by photovoltaic effect. So with the help of this photovoltaic effect, we can get to PN junction diodes, and with the help of diodes, we can get transistors also. You will get PNP transistors and NPN transistors. First, we have to understand the concept involved in that, right? There is a zero bias system condition or forward bias condition or backward bias condition. Forward bias, backward bias, and zero bias conditions. Means that is simply with respect to the connectivity only. That is simply with respect to the connectivity. Based on that connectivity, what is the forward bias, what is the reverse bias, and what is the zero bias. With the help of this, we have to understand that photovoltaic effect and making the output diodes and transistors. A PN junction diode can be prepared, right? How we have prepared this PN junction diode means N type of semiconductors is connected with the P type of semiconductors. In N type of semiconductors, we have negative ions. These all negative ions will be on this side. And in P type, the holes will be there, that is positive side. This positive and negative ions which will be come closer and make a depletion layer. So this is the depletion layer, or depletion region. In the depletion region, positive and negative ions should be present. Here just we have to see when zero bias will be occurs and when forward bias will be occurs and when reverse bias will be occurred. So this is the N region containing negatives. This is the P region containing positives. So we are preparing PN junction. These negatives and positives will be make a depletion layer. This is the yellow region will be depletion layer. And these two are connected additionally with the positive battery. Means externally we are adding, not in a circuit. Not in this circuit. So the circuit will be completed and one part will be one of the position will be connected with the N terminal and P terminal. So at that time, this can act as the zero bias. If we have to utilize that external battery and connectivity will be, so N type will be connected to terminal or P type will be connected to P terminal. That can be one kind of the bias. And if N terminal is connected with the P region or P terminal is connected with the N region, that can be other kind of biases. So that are what forward bias and backward bias. Right? So just we'll see the diagrams of forward bias and backward bias, and then we'll discuss about diagram. See, in previously, PN junctions will be connected and immediately one depletion layer is formed and the two will be connected with external battery outside. But here, P terminal is connected with the P type semiconductors. Right? Means positive terminal is connected with the P type semiconductors. Negative terminal is connected with the N type of semiconductors. Such type of connectivity produces forward bias. In reverse bias, N terminal is connected with the P. N terminal is connected with the P type, and a P terminal is connected with the N type. Right? So that is the reverse. Same kind connectivity is there. Negative terminal N type, positive terminal P type. That is the forward bias. The reverse connectivity will be negative terminal with positive and positive terminal is connected with negative. That is the reverse bias. Zero bias, reverse bias, and forward bias. So in that breakdown voltage also will be occurs. So that is the breakdown voltage will be explained with the help of following diagram. Let's see this diagram. Based on that connectivity, so this is the region will indicate what forward bias. Forward bias means simple. P terminal is connected with positive. N terminal is connected with negative. P connected with P, N connected with N, that is a forward bias. If reverse bias means, right, P is connected with N terminal, N is connected with P terminal. This is the reverse bias. And zero bias means it is both the diodes are connected with external, that is not in the circuit battery. Here, current versus voltage. If we plot a graph between current versus voltage, we can get this is the arrangement of forward bias with knee temperature, means knee positions, and this is the breakdown temperature where the suddenly change in the current will be occurs. So that is the forward bias and backward bias. These two will be represented with this diagram. Right. So this will be included all kind of biases. So then one more topic is there, superconductivity. Okay. So let us do superconductivity. What is meant by superconductivity? Right. So superconductivity state is nothing but zero resistivity state. What we may call zero resistive. Generally, conductance are like how will write the conductance? Conductance is the reciprocal of resistance. Conductance is the reciprocal of resistance. This is the 1 by reciprocal, 1 by R. If resistance is becomes zero, resistance is becomes zero means the conductance becomes infinity. Whatever is the material whose resistance will be approaches to zero, that material such infinite conductivity. Am I audible? Yes, anyone. Am I audible?
Yes, sir.
So I can share the notes, no issue. Just you go through the how I am explaining all those parameters. Just you go through the notes, you can understand easily. Because mostly theory part will be there. This is a solid state and nanoparticles. So it is easy to understand the concept only. Just go through the terminology, how I am approaching all those things. Okay. So conductivity means, right? Resistance, reciprocal of the resistance becomes conductivity. Reciprocal of resistance becomes conductivity. Right. Whatever is the substance is there, whose resistance we have to reduce it to zero. So once the substance reduces to zero, resistance is reduces to zero means conductance becomes infinity. Whatever is the material showing infinite conductivity, so that is known as its superconductivity nature. So what is meant by superconductivity nature means the material possesses infinite conductivity at a zero resistance. Okay. So the simple definition, the phenomenon of exhibiting zero resistivity or infinite conductivity is known as superconductivity, and such material is known as superconductors. Even these are acts as superconductors at a high temperature also. Therefore, we have to discuss about high temperature superconductors. There are various kind of materials will be there in high temperature superconductors. One of the well-known material that is 123 material. So those 123 material is access superconductor material that is has the composition of lithium, barium, and copper with oxygen 7 minus X. Why Ba2CO3O 7 minus X. So that we will discuss later on about superconductor. Right. So we discovered the superconductivity first one, that is HK ohms. Like HK ohms discovered the superconductivity. So in case of resistivity of the mercury metal. Mercury is a liquid metal, right? It is a D black element, right? D black element whose atomic number is 80, and in out of all the D black elements, only mercury is the liquid metal, remaining all are solids. Right? This mercury metal will be vanished abruptly at 4.2 Kelvin if the temperature will be decreases, right? Temperature will be decreases. So as the resistance will be reaches to zero, means at any temperature or else at a particular temperature, the resistance of the material becomes zero, means so such temperature is known as its critical temperature. And at that critical temperature, the material becomes shows infinite conductivity. At that critical temperature, the material shows infinite conductivity. Such infinite conductivity phenomenon or condition is considered as superconductivity state, or the particular state is. Particularly for mercury metal, the super that can shows a infinite conductivity at 4.2 Kelvin. 4.2 Kelvin. So this is when we see. If we see or if we observe that, right? So here temperature versus resistance. Temperature versus resistance, we have to plot a graph. So here initially each and every object has possessed some resistance because resistance is directly proportional to L by E, length of the object and the area occupied by the object. Resistance is directly proportional to length by area. Resistance is directly proportional to length by area. Right? So therefore each and every object in the universe has some resistance value. Right? That is at particular temperature it has some resistance. As temperature is decreases, the resistance also will be decreases, and suddenly one temperature, the resistance becomes getting zero. Such temperature is known as resistivity will be zero, means possess infinite conductivity. So such phenomenon is known as what? Superconductivity phenomenon. Whatever is the material whose temperature we have to reduce, and at one certain temperature, the resistance of the material becomes zero. Hence, that particular temperature is known as critical temperature of that material, and at that temperature, the material shows infinite conductivity. The material shows infinite conductivity. So here we have to see the various kind of materials will be produced, right? So just to see the critical temperature of all those materials and how it should be varied, right? So aluminum will be shows at a very low temperature, that is 1.19 Kelvin. So if you may consider the aluminium, whose critical temperature will be what? 1.19. At that particular 1.19, aluminium will be showing a maximum or infinite conductivity. Coming to the part of mercury, mercury will be 4.15 and lead will be 7.2 and molybdenum will be 0.92, cadmium like that. The combination of niobium and tin, niobium and germanium. After that, just now we told that there is the 1, 2, 3 materials, that is why Ba2CO3O7. Right? One yttrium, two barium, three coppers combined with oxygens that can produces 90 Kelvin. At 90 Kelvin, the resistance of the material becomes zero. Hence, that is the state is known as superconductivity state. Hence, that is the state is known as superconductivity state. So the superconductivity state of various metals will be given based on the resistance on. At that particular temperature, the resistance of the material becomes zero. At that particular temperature, the resistance of the material becomes zero. Hence, that can shows a superconductivity. Some other metals also will be there, right? Materials. So somehow showing even higher temperature than the 1 to 3 materials, like the combination of various metals and non-metals. These all are metals only, right? The combination of various metals that can give high temperatures superconductivity edge. So if we see, there are how many kind of, right? How many kind of superconductivity materials will be there, and that will be explained even not only with the temperature, even with the help of magnetic field also we have to identify. So means the description of superconductivity by magnetic field means, as we mentioned, that at what temperature the material becomes showing maximum conductivity, means infinite conductivity. So such condition is known as superconductivity state. Which is similar to the TC, there is a critical magnetic field strength is there. Means if we may apply magnetic field to that material, at one particular magnetic field, the resistance of the material becomes zero and whose possess infinite conductivity. Means with the help of magnetic field also we are observing that superconductivity state instead of temperature. Therefore, two parameters are essential to express that what kind of superconductivity nature will be there. There are two kind of superconductivities will be there. One is the type 1 superconductors and the other is the type 2 superconductors. Right? So what are meant by type 1 superconductors and what are meant by type 2 superconductors? So that we'll see. This is in diagram. So as we have discussed for the temperature, right? How we got the temperature diagram, right? Let's see. The resistance will be decreases and at certain temperature that becomes zero. Therefore, this is the temperature is critical temperature where the resistance will becomes zero. Such condition is known as superconductivity state. Now, if we plot a graph between temperature and the HC, at this particular temperature, what is the magnetic field strength? That is known as HC. This is the critical magnetic field. HC is the critical magnetic field strength. Right? Critical temperature are so critical magnetic field. With respect to these, we are going to express the various kind of the superconductors and how we are going to prepare superconductors, types of superconductors like type 1 superconductor, type 2 superconductors, and what is the crystal structure of the superconductor material of YBA2C3O-6 and what is its phase diagram and what are the applications and what is the superconductivity nature, high superconductivity nature in particularly two types. All those things we will be discussed in the next class. Followed by emission effect and so some other topics will be there that will be discussed in the